So this is a report on joint work with Agnes Beaudry, Bobkova and Goerss. And I think there have been, in the last few years, several talks on this subject. I don't think I've given one on that, on various stages in this work on progress. So I apologize to all those who have heard a fair amount of what I'm going to talk about before, but I think there's been enough turnover that maybe there are also a substantial number of people here who have not really heard much about that before. The difference between previous talks and this one is that so far we had information about these things in the title, which I'm going to explain, and I think this will be the first talk where I'm ready sort of to say exactly what the structure of the group is that we're talking about. Okay, so let me start with some background. Hopkins, Picard groups. And what we know about them. So I think with this audience, even though sort of varied backgrounds, I think I don't have to say very much about or motivating much about chromatic homotopy theory anymore. So we look at Kn local, so we fix we have two parameters, n and p, and a natural number, p prime, and we look at the prime p, and we look at Kn local spectra at p. They form a symmetric monoidal category, a smash product where you have to relocalize in order to get an internal smash product. And you can look at invertible spectra, the unit being the sphere, the Kn localization of the sphere, and they form a unit which we call Pic and P. So that's isoclasses, so homotopy equivalence classes of Kn local invertible spectra. So that turns out to be a set and therefore a group. Not up to completely trivial, that's a set, but it is. And so we'd like to understand them. The sort of interesting structural invariance of this category. I'll give maybe some other justification just in a couple of minutes. One way of studying them is if you have an element in there, you can associate to it its Morava E theory. So I recall that Morava or imitate E. So Kn is the Morava K theory, because we're not saying it. And then there's a Morava or imitate theory. It's a complex-oriented theory, which is in some sense a lift of Kn. I don't want to say much about it. So that's a rich thing. I mean, that's a module. In fact, we can actually, it's a theory, but we can just look at what it's a two-periodic theory. And invertible spectra are either concentrated in dimension, in even dimension, or in odd dimensions. And if I can restrict to those which are in even dimensions, then it's sufficient to look at just what happens in degree 0. And this is a module of a huge power series ring with n-1 generators. And it has an action of a Morava stabilizer group, which is a huge profiler group. And for most part of that talk, you don't really have to know any details about it. Okay, and so that's so that.
Can I so if you shift and look at E2 instead, how does that change the GN action?
It does change the GN action. I mean, so the two sphere and the zero sphere, for example, are not the same.
Yes. So how does it change?
Well, it changes. I mean, so the whole thing is.
Does it only?
I mean, the whole thing is a module. If you look at the greater thing, it's a module over this little with this power series, with this periodicity generator acted on, and then the unit, I mean, sort of you understand this action. Give me, I'll come back to the question.
So U is the invariant differential with the formal proof, so, and G is the automorphism, so it just twists by the action of the invariant differential.
So in fact, these modules form an algebraic Picard. Okay? There's an algebraic Picard group. Of tensor invertible modules. This is structure. This is structure. Here you have it's a module over that. It's a profiling module over that. Has a compatible GN action, and the monoidal structure is given by tensor product over E sub. And you can try to study this Picard group by, so the results of homomorphism from this group. And now I'm looking at an index 2 subgroup. I'm looking at those which are concentrated further, or other modules concentrated in degree 0. And then that goes to the corresponding algebraic Picard group. So I have too many declarations upstairs and downstairs. That's it. And this can actually be expressed in terms of H1 of Gn, which acts on the unit. So it's it's something which is completely algebraic. In principle, you can try to calculate it. Sometimes you can calculate it, and this is a kind of first approximation to our topological Picard group. Well, so maybe one more word while we're interested in that. I mean, the interest, one further interest, rather than the important structural constant, comes from Goerss-Hopkins duality. Which various people have been talking about during this event here. And so there are important elements in this Picard group. One is given by the sphere, or by the two-sphere if you concentrate on things which are in even dimensions. The other one is by the thing which is called the determinant sphere. We have talks on that. And then there is the guy which is called the Poincare dual of the sphere, whatever that is precisely. This is not really the subject of the talk, but there's a formula due to Goerss and Hopkins which says that this is the same as this. So if you want, I mean, there is a relation between these three, between the three spectra, except that this is a relation not on that level, it's the image in the algebraic Picard. So the kernel of that map sort of gives a correction term, or there can be a correction term which is in the kernel of this map, and that's kappa. And P is the kernel of this homomorphism that's called an epsilon for evaluation. So that's the exotic subgroup in the Picard. Yeah. So that's what we're interested in, and in particular we're interested in that. Okay, so so just a little more background to give you some feeling about these objects. So this group is complicated because this is a complicated module. It's a power series ring. This is a complicated p-adic analytic Lie group. So that is something which is complicated, but some of the cases, and so the question is, I mean, how can you understand this group? Well, there is an approximation to it proposed by Hopkins. This group Gn contains, that's a group of units in a division algebra. The division algebra contains the unramified extensions over the p-adics, and in the units you have the units of the bit vectors. So these are the bit vectors over the field with p to the n elements. And in this E0 star, you also have bit vectors. So here I should have said that here. I mean, these are bit vectors over fp to the n. And the ideal channel by u1 up to un minus 1 is stable by this group. And so if you quotient by it, you get into this, and you end up in the Galois invariant part. That's easy to check. And so that part is much, much easier to understand than this part. And that's sort of your first approximation to this part.
This group cohomology, is that as a pro-algebraic?
It's a continuous group cohomology.
Is it as a pro-finite group or as a pro-algebraic group?
It's a profinite. And so this one, okay, so then what's known? Well, it's known that, let's see, what did I say? It's known that kappa np is equal to so if for fixed n, well, if n is fixed and p is sufficiently large with respect to n. So in fact, the algebra sort of captures everything if for fixed chromatic level as soon as the prime is large enough. So the question is what happens at small primes. I mean, that's what the interesting thing is. One can be specific, I mean, for given n, I mean, how large p has to be, but that's not very relevant for the talk. This gadget is known, well, I mean, I think this gadget can be calculated for every n p, but what's interesting is that I don't have a name for this one, and we call it rho for restriction. So this map, in all the cases where we know that, okay, so what are the cases where we know that? For n equals to 1 and any prime, we know both sides and rho is nice. Okay? And so you can actually figure out this by just looking at the right-hand side. Maybe that has an exercise to you. If n is equal to 2 and prime is bigger than 2, then rho is nice. So I should give some names here. This is Hopkins, Sadowski. This is unpublished work by Hopkins. And there's a thesis of a student of mine, Ladere, who does that for p bigger than, I think both of them, p bigger than 3. And then there's Kalmano, well, no, there's work with Goerss with Morava and West, just for n equals 2 and p equals 3. And again,
what is the statement? Rho
is an isomorphism.
What's an isomorphism?
If p is equal to 2, then rho, the kernel of rho is sigma 2 and rho is on 2. And I gave a Gongshu talk on this subject 2 months ago, maybe. These were the confusing and surprising picks. Remember. Okay, so that's what we know about the algebraic Picard groups. We don't know much more, I think. I think that's basically what we know.
In the first thing, if p is large with respect to n, is then epsilon subjective?
That is not known. The composite will not be subjective. The composite of epsilon and rho will not be subjective. That is not the unpublished work of Mike. In fact, I mean, for the composite, it looks as if there's only these two guys. Okay, so that's background on the algebraic Picard group, and so as I said before, the focus of this talk will be on kappa 2, 2. I should also say, I mean, of course, once you've calculated kappa NP, once you've calculated epsilon, or epsilon rho, the composite, you might have a short exact sequence, and there are questions, is it split or not? And so far, there are basically only two cases where we understand, I mean, non-trivial cases which we've analyzed. That's the case n equals 1 and p equals to 2. I should say something about kappas. So we said this is trivial if p is large enough for fixed n. So what is known else? I mean, if n is equal to 1, we know that kappa 1 is trivial if p is bigger than 2, so p odd is large enough. And it's C mod 2 if p is equal to 2, and it's again closed off. And the sequence is not split. If n is equal to 2, kappa 2 is 0 if p is bigger than 3, and it's C mod 3 squared, and so that's again with Paul, with Mark, Overl, and Hans-Werner. And the question is what happens if p is equal to 2. I'm going to give the answer. Maybe not in this tiny little spot somewhere. More prominently on the blackboard. Okay. Okay, so that's what I will be focusing on. Part of what I'm saying will be true for channel N and P, but whenever it comes to something really concrete, it will be N equals P equals 2 from now on.
Somehow you gave as motivation that the isomorphism down there did not hold at the spectrum level, so in the case where the kernel is non-trivial.
Right. So there is another question, what is the correction term?
Yeah.
So we know what the correction term is if n is equal to p equal to 2. It's a unique non-trivial element in the kernel.
Okay.
If n is equal to 2 and p equal to 3, there is a correction term, and we've identified it. I looked with Paul and Paul. And it's one of the two copies of the C mod 3, but so this C mod 3 squared, it's sort of, there's no canonical, I mean, basis, if you look, I mean, it's a vector space over field with 3 elements. It doesn't have any canonical basis, and so, but there is a unique element in it which you can specify, and which you can also use to give a basis, if you want. I mean, part of the basis. The other part is sort of canonical.
So you also said that when you have the C mod 2, the sequence is not split.
Sorry?
You said that when you have the C mod 2, the sequence is not split.
Right.
Can you say what the extension is?
So if n is equal to 1 and p equal to 2, you have pick 1 maps to pick 1 algebraic, which is to this. In fact, you should think of that as the endomorphisms of G1. The endomorphisms of W, well, of W in that case is the p-helix itself. It's the bit vectors of Fp. So the H, well, there's no Galois group in that case. So the H1 is just the endomorphisms of Cp star. For C2 star, abstractly, that's isomorphic to this. And there's a kernel C mod 2, and this group is isomorphic to C2 cross C4 cross C2. I haven't completely specified the extension if I write it down like that, but I mean, I have told you what you have. I would have to tell you more about the elements in this exact sequence before I can really specify the extension. I mean, this guy is usually called the choker, and the choker has sort of a square. Okay. Okay. So how can you study kappa? So there will be filtrations on kappa. So I think that was the first chapter, which was background. Filtrations on kappa. So the element in kappa is a spectrum for whom the stabilizer group doesn't recognize. Well, stabilizer group, it thinks it's a C. Okay? So if you look at the homotopy fixed by, well, if you look at the Adams-Novikov spectral sequence, somebody in there, then the E2 term looks precisely like the one for the sphere. So it's ENT, but ENT. And so this guy has a Morava motor which is isomorphic to that. So it has, once you fix an isomorphism, you have an element in S equals T equals so, which is a G n-equivariant element in E so, and that corresponds to the unit if you have the sphere. It's not unique, but you choose one, and the sequel of the construction will be not dependent on a choice. And so if this guy is a permanent cycle in the spectral sequence, then you get a map from the sphere into X. And that map will be in equivalence. And then your guy will not be fake. It will be the real sphere. Okay? So the differentials in the Adams spectral sequence on this class are sort of obstructions for X being equal to the sphere. So in fact, you can construct a filtration on kappa. So you take all those for which the first R differentials, well, the first I differentials for 2 lesser equal than I less than R are so. Okay? So this defines a decreasing filtration on kappa. Kappa is kappa 2, and this filtration. It's a decreasing filtration. One knows that this spectral sequence has a universal vanishing line at E infinity, so therefore this filtration will be decreasing filtration, which will be finite. A priori, we don't know when it stops, but and what's also known in general is that the filtration quotients, well, there are sub-quotients of the E2 term in the corresponding spot. So you have, in fact, the direct sum of kappa r divided by kappa r plus 1 injects into, more generally, into E, the direct sum. But it's a finite sum. That's the target group of the differential. And these are sub-quotients of E2, and one knows that E2 is a profinite group, so we know that kappa is a profinite group. It's conjectured to be finite in all cases which we understand concretely. It is finite, that we don't know in general. Okay, so that's the first filtration, which is very useful. So that's the standard Adams-Novikov filtration. Now there's a second filtration, and for this, which uses subgroups of GM. Filtration using closed subgroups of GM. Well, more generally, if you take for T any test spectrum, you can define kappa lower T. So that's all that X in kappa, such that X smash T is equivalent to T. That's a subgroup. And in fact, you can sort of take appropriate type n complexes. It's a finite group. It's a subgroup of finite index, and kappa is a topology coming from these. I mean, kappa a priori is a profinite group, and the topology comes from these subgroups. Now, the test spectra we are interested in is, so if F is a closed subgroup, we have that, I don't have to call it. F is a closed subgroup. I will define kappa F to be kappa E H F. So F is a finite subgroup of the stabilized group. The stabilized group acts on the mutate spectrum, so we can form these homotopy fixed points, and I take these homotopy fixed points as a test spectrum. So F could be finite, but it could be infinite. Okay. So, for example, well, it's clear that if F1 is contained in F2, then kappa F2 is contained in kappa F4. That's an elementary observation. There are two extreme cases. If F is equal to G2, and using the fact that the homotopy fixed point with respect to G2 is the sphere itself, then kappa F is just the trivial group consisting just of the localization of this field. Okay. And if F is a trivial group, then kappa F is equal to kappa. Now, unfortunately, I mean, you might think, well, okay, great. I mean, now we have all these subgroups to test, but unfortunately, there aren't that many really which seem to be useful, which have been useful so far, or which have been necessary so far. I'll take more positive attitude. You can look at finite subgroups, and then there's one infinite subgroup which plays an important role. That's the kernel of the reduced norm, roughly. So, so in fact, if Fn is Gn, take the unique maximal finite P subgroup of Gn, so that's unique up to conjugacy. Then what I'm interested in is kappa Fn. Contained in kappa, and there is kappa of Gn1, and Gn1 is the kernel of the reduced norm. So there's a homomorphism from Gn to the units in the p-adix, and if you divide out by the subgroup of elements of finite order, and you get something which is abstractly isomorphic to the p-adix. And this is just a kernel. Okay. So that these are the things which have been useful in the cases we've been looking at. If n is equal to 1, this is all the group. So this is nothing interesting. If n is equal to 2, then I mean cases applying 2 and 3, actually this group is sort of the important group.
What is the unique?
The magic word is Kohlenmörtel. Okay. So if n is equal to p is equal to 2, then f2 is, okay, f2 would be q8, and you can actually sort of, for the purpose of studying kappa, you can work with q8, or you can extend this and make it a maximal subgroup. And then it's contained. Well, it's Q8 if you look at this. If you look at the at Sn rather than Gn. Otherwise, it's a group of order 16. So I'm going to get bogged down by details here. 48, which, depending on your form of the formal group law, is either GL2F3 or the binary opposite. And then obviously you can see over the 8, so the 2 single subgroup is not, cannot be Q8. That's a fine detail to think about. Okay, so theorem. Now n is equal to p is equal to 2. Kappa G21 is isomorphic to C mod 8 plus C mod 4. Kappa G48 modulo kappa G21 is isomorphic to C mod 2. And kappa modulo kappa G48 is isomorphic to C mod 8. Okay, I can try to give an outline. So I think talks that I've seen, or at least seen parts of it on the internet, and we've gotten that far, I think. The question, of course, then is, I mean, what happens to the filtration? Okay? So that's the new part of this talk.
Also, do you have a way to give generators in these groups?
Good question. That our understanding is not perfect when it comes to that at this point. So the first part, so there are 3 parts, A, B, and C, and there are 3 statements. So part A is sort of, that part is sort of the, we started talking about exotic elements in kappa, and then at the prime 3 we found out there are things which are more exotic than we expected them, so we call them super exotic. But now we have a filtration once more, so we have highly super exotic, I don't know exactly. So these are the extremely super exotic, but they turn out to be the easiest to understand in some sense, okay? In retrospect. No? First, if you don't think about them, you don't even see them. I mean, in fact, you don't see them for n equals 1, but they are easy to understand. So they come from, there's a general result. You can describe kappa Gn1. You can give a general description of that, and the question is how explicit is it? It's isomorphic to H1 of this quotient group, Gn modulo Gn1, so it's a PLX. This is isomorphism. And you let that act on something which I call Kn. And Kn is the kernel of the map of the, from pi 0 of EHGN1 to H0, so it's a kernel of the H homomorphism with the sense vector sequence. I mean, a priori CP acts non-trivially, I mean, can act non-trivially on that. There's no reason why this action should be trivial. But there is this general description, so I should add here the name of Craig Westerland, who has also observed that. And so if you are able to calculate that, and this, and if you can get your hands on Kn, maybe you can find out also what the action is, then you're actually in good shape. And that's actually what happens in this case. K2 is equal to that group and the group X, and the action is true. And there's a nice map. I mean, if you have an element here, if you have an element in Kn, so this in fact is nothing else but the co-invariance. Each one is the co-invariance with respect to this action. Okay? So if you take an element in lambda, then you can check that it only depends on its orbit, then you can associate to that the fiber of the map between EHGN1 to itself. And if you take the sphere, you would take some kind of Adams operation minus the identity. And here you take the Adams operation minus lambda. And that kernel is sort of the associated element in kappa. Okay. So that part is sort of, I mean, well, the hard part is calculating K2. And that's essentially, that's in a paper with Paul and with Agnes on the chromatic spinning projection. Now the case, so that's A. So B, I'm going to say much less. I think that because I have nothing new to say on that, and the story is not that easy to outline, even outline.
Can you raise the other board so you can see?
So for B, I mean, so you have an element you have this CMOD 2, and then I have to, I think I can't really go into that otherwise. I mean, so now I haven't talked about the resolutions that we've been playing with at n equals 2. I mean, there are various resolutions we can use to study LKN, I mean, the KN local category study. Try to understand pi star of LK2, pi star of LK2 smash some pseudo-finite complexes. Resolutions which have been used at the prime 3 with great success to settle all these questions on chromatic splitting, also for P equals 2, on calculating the Picard proof and determining the correction term in the Baum-Conrad's duality formula. So these things come up when you so I'm going to write something which is not in print, but I think it's true. Yeah. So there is a resolution of the homotopy fixed points with respect to this. What's in print, I mean, this contains the S21 is index to subgroup. What's in print is for S21. And these are homotopy fixed points for well understood finite subgroups. And not only are the finite subgroups well understood, also this homotopy fixed point spectra are well understood. And you can use that to study pi so E, so HGN1, and you get K2 out of this analysis. And this element CMOD 2 in the second statement is quotient kappa G48 or kappa G21, G21, that comes from an element in pi minus 1 of this. And you can use this to twist, to perturb this resolution and construct an E2HG21 module, which is a first step towards constructing an element in kappa G48. And then you have to upgrade this guy to something which is really invertible in the Picard group of K2 local spectra. So here you twist a topological duality resolution to get a fake E2HG21, and then you promote it to a fake LK2. So that's subtle, but in some sense it's still constructive. I mean, you start with this spectrum, you twist the maps, and you verify that the things you want to do can be done, and you end up with some spectra where you have some kind of handle on it. The last part, which is sort of the part which is sort of the least exotic from the historical perspective, which was supposed to be there right from the beginning, that's sort of the most elusive when it comes to really describing it concretely. It exists for theoretical reasons. It exists because of three things. There's no explicit construction of the representative in kappa modulo kappa G48, but we know that there must be an element which in kappa which maps to this general element, which is C mod 8. The reason for that, I think there have been talks, I think, on that is coming from this formula of Hopkins-Goerss, which you can write like this. So that's the formula if you have no correction term, and Pn is defined by this equation. So that's a correction term in kappa n. It's a unique element in kappa n which has this property. And then there are two important ingredients. One is due to Irina, which determines the span-divided dual of G48. This is the sigma 44 of EHG48. Maybe Irina is giving a talk on that, or somebody. This has come up at some point. And then there is another one, which I call BC1, so the Brown Combinates dual of this guy. That's supposed to be sigma 22 of EH G48, and as far as I know, this is not in the literature, but it's known, and nobody, I mean, none of us questions it. There is something which is also not in the literature, but it's about to be written up as if you look at the same thing and smash it with one of these type 2 complexes, which we call A1, whose cohomology, I mean, these are finite complexes, 8-cell complexes, whose cohomology over the Steno-Large is isomorphic. I mean, this is A1 as an A1 module. Then you, if you put in, if you give yourself that this has to be, at least some of these are self-dual. If you pick a self-dual one, if you use the information that this has to be a suspension, and by looking at the homotopy groups, you can figure out what this suspension is, and it's this. And if you feed these two, I mean BC1 or BC2 and D into this first formula, then you find out that something like, if you do it with the first one, you get sigma 2 E2 HG48 smash is isomorphic, is equivalent to sigma 46 EHG48 smash P2. And there we are. It doesn't reproduce it, it reproduces it only up to suspension. The suspension is 24, which is 1/8 of the periodicity of the spectrum. That explains the C mod 8. But it's
G48 is a subgroup.
the G48 is a subgroup of G2.
Is it the torsion subgroup?
Well, I mean, there's no unique torsion subgroup in G2. I mean, it's not an immediate group. Can conjugate things around.
It's not a normal subgroup.
It's not normal. It's not normal. I mean, other than G21, they're congruent subgroups, but subgroups tend to be somewhat congruent subgroups. Okay, so I don't want to say more about that. I want to say a little bit more about the remaining 10 minutes, 15 minutes. I want to use discussing the extensions.
But is it a maximal finite subgroup?
It's maximal up to contrast. I mean, it's unique maximal up to contrast.
Does it have a normalizer that's bigger than itself?
Yes.
And does that trivially, or how does that act on these suspensions?
I don't know by heart what happens with P equals 2. And for p equals 3, you have, for example, you have a similar phenomena. You have a group of order 12 or 24 if you look at the full. Well, let me write 12 because then I know that my writing is correct. And then if you look at the normalizer of this, well, so this group contains, the crucial thing is at the prime 3 is the 3 part of this group. So if you look at the C3 in there, the unique C3 in there, which is normal in there, and if you look at its normalizer, this sits in a vibration like this. So you can build it for the normalizer, you can build it out of this finite subgroups. And in fact, the very, very first part on all this story about resolutions is closely related to that observation. But that's sort of, I mean, when it's not topic, right? I mean, you ask the question. Okay, so theorem 2 is the filtration splits. Kappa is isomorphic to kappa modulo kappa G48 plus kappa G48 and kappa G48 is isomorphic to kappa G48 modulo kappa G21 plus kappa G2. So I prefer to write it like this rather than writing sigma 8 plus sigma 8 plus sigma 4 plus sigma 2, because in this way you have some information on where the summits come from. Okay, so why do they split? Well, the point is that, I mean, so far I've talked about the standard Adams-Novikov filtration, but there are other filtrations of kappa. And they're playing with these other filtrations on kappa. You can sort of unlock the truth about the extensions. So in fact, I mean, I did talk about this other filtration which is related to the finite subgroups. But I mean, so the theorem 1 was coming from looking at the filtration by the closed subgroups, the filtration by the closed subgroups, and it gives this associated gradient. And now we look at the filtration coming from the Adams-Novikov spectral sequence, and that will allow us to split the second sequence. The first sequence will not be, I mean, we'll still need to do something else for the first sequence. So now the question is, what do we know about the Adams-Novikov spectral sequence? So by using the topological duality spectral sequence, by using the topological duality resolution, which comes from an algebraic duality resolution, gives means to calculate homology of G2 with coefficients in E2 at least. We have not tried seriously, but it's certainly very hard to do that in complete generality. But we are only interested now in things of the groups of the type, interested in these kinds of groups. Okay? And first of all, because this is evenly graded E, we see that these groups are non-trivial only if F is odd. Okay? And so for the first differential in the Adams-Novikov spectral sequence, the recipient of the differential is H3 with coefficients in G2. So that's the recipient of the first differential. And by using the duality resolution, which first gives the cohomology for G21, but then you sort of promote it to G2, you get that this group is isomorphic to an elementary group, generally by two elements. And because of time has progressed, I think I'm not going to give you the generators. So you calculate that and you find out it's C12 plus C12. And then you calculate H5. That's the next one, which is of interest. And that turns out to be, and that's sort of, we like that. Because somehow we know, we've calculated enough that we know what pi minus 1 is of this homotopy spectrum, of the K2 local sphere. And ideally, the elements in pi minus 1 are give you the size of kappa. But that's in an ideal world. Huh? I mean, because there's no guarantee that the approximation I wrote down before, that the direct sum of the ERs is isomorphic to the associated gradient of the filtration of kappa. This is just an injection. But we sort of expect that, and we sort of know enough that we know that these two elements are realized by differentials. Now at the next level we get something which is C mod 4 plus C mod 4 plus C mod 2 plus C mod 2. And that's too big. What we want is that much. And in fact, we can determine the D3 differential, and the D3 differential disappears by D3. Because we are not really, I mean, it's not really that we're interested in. We are interested in the D5 term, for the D5 differential. So we have to do one differential in the isomorphic spectral sequence, and that actually reduces this in size to the size that we want. And then there's H7. And that turns out to be elementary abelian of rank 6. And that's way too big. You only want that. But in fact, I mean, D3 reduces it. Already D3. I mean, we don't even have to go up to D7. I mean, we don't have to calculate D5. D3 reduces to C mod 2 squared. Oh, and wait a second, I've cheated. I've cheated. Something which isn't right. Right, so this is. There is one more copy of C mod 2. And this copy persists to the E5 term. And this copy shows that, in fact, I mean, if you believe everything else I told you, that in fact the approximation by the ER terms is really not an isomorphism, it's sort of it's an injection. This guy disappears in the spectral sequence for the sphere by D23. So it's sort of it's really stubborn. It stays. Okay. But those here, the four guys disappear by D3. Okay, and then with that in hand, it's not hard, and I'm not able to give the details, but it's not hard to, so in fact, you can say E5 is C mod 4 squared plus C mod 2, and here E7 is isomorphic to C mod 2 squared. Now, if you look at the sizes so far, so this is for 2 to the, I mean, if you look at the logarithm to the base 2 of the cardinal, you have 2, you have 4, plus 1 is 5. No, wait a second. Oh no, there are C mod 2 squared here. Right? So you had 2 from here, you had another 4, plus 2 makes 8 together altogether, and here you have a 10. The group that I described is order 2 to the number. Okay? And in fact, I mean, you can show now that kappa to the 8 is equal to 0. By knowing what we know about the Adams-Novikov filtration, by using what we know from the other filtration by finite subgroups, you can sort of identify the elements, I mean, filtration quotients in kappa modulo kappa 8, and we see everything is detected in kappa modulo kappa 8. And then if you look at the inclusion from kappa 4, so that means those elements in the -1 line of the Adams-Novikov, well, that means those elements for which D3 is trivial. So that's subgroup in kappa, and if you look at this composite, this map is on. And on the other hand, if you look at the filtration, if you look at the direct sum of those, or the possible extension, you see what you get from kappa 4, every element in kappa 4 will be annihilated by 8, because it's an extension of this group by this group. Maybe the other way around, but any element is killed by 8, and that gives a splitting in part. Which one? The first splitting. So first sequence splits. Now the second sequence, you have, now you look at kappa G48. What? Look at kappa G48. You know the other stuff splits off, so it's enough to understand kappa G48. So we have this short exact sequence. And you just sort of know, I mean you can list what are the possible abstract groups which fit into such an exact sequence. You could have C mod 16 plus C mod 4 plus C mod 2, or you could have C mod 8 plus C mod 8, or you could have the direct sum.
I don't think this is E2.
Not the first one.
Well, then there's nothing. Okay? So that's the possible abstract groups which can fit into such an extension. Now, if you can prove that this group is annihilated by 8, then the first one is out. Okay? And we can, I tell you the second how. And then the other thing is that if you look at the Adams-Novikov filtration, we see that the generator, this C mod 2 is detected on the 3 line, and the generator for this C mod 4 is also detected on the 3 line. And there's no extension on the 3 line. The 3 line is annihilated by 2, and that rules out this one. So this one remains. So the question is, why do we know that 8 annihilates kappa G48? So in kappa G48, you have spectra which, after smashing with finite homotopy fixed points for finite subgroups, are standard. Okay? So that means if you look at the central isoresolution, the duality resolution, the spectra appearing in the resolution are the same as for this field. But the duality resolution is not good enough to help us here. We have already used it, and it was very helpful to begin with. But now we need the topological centralized resolution. So that's another resolution which actually resolves the K2 local sphere. All of the K2 local sphere, now it's 4 spectra. Each of them are wedged as a homotopy fixed point spectra of the finite subgroups. And the finite subgroups which are, I mean the spectra which are occurring are 48. They are C4, they are C2, and they are C6. Those two guys appear here and here. And everything which appears here is from those. And if you look at the duality spectral, at the spectral sequence associated with that, that's a little spectral sequence. If you write it as Adams-Novikov type spectral sequence, it has 4 rows. It's trivial here for here, and so it has here the homotopy of y0, then here shifted the homotopy of y1, y2, y3, and y4, and you're interested what happens here on this row. You want to understand, because there's a similar filtration now as if you had the ordinary Adams-Novikov spectral sequence. And now the contributions by these homotopy fixed points in all these degrees is annihilated by 2 each time. And how many? And we only have to look at D2, D3, and D4. So the group is annihilated by 8. That's
All the questions.
So there's this homomorphism from the Picard group to the units inside pi 0 of the K2 locus here that tells you like how bad the Koszul sine rule is for your thing. You know how big the image of the Picard group is?
So this Morava EN, so now you work over the field FP, but you can also do larger fields.
Yeah.
So does that give you a way to get some extra structure on these groups, like modules of Picard or something?
No, I don't think so. I mean, you can go to a higher Lubin Tate. I mean, you can extend the field over which the formal group lives that you start with, but then you build in the Galois. I mean, if the formal group, you want to look at the formal group which is defined already over the prime field. And then you can sort of extend coefficients. You have to extend coefficients up to FP to the end to get the full stabilizer. If you go further, the automorphism group of the formal group over the field sort of remains the same, but Gn has the Galois group incorporated, so that sort of becomes bigger and bigger. And if you look at the homotopy fixed points, it cuts it back again. And also, if you look at the algebraic Picard group, you would have to look at some bigger group acting on the units in some bigger ring. But there will be, you can use that to show, for example, that it doesn't depend with which formal group you start, because it can go up, compare up there, and then go down again. But I think that the form that you asked the question, I don't have positive news.
I mean, it's just, I wonder how useful it can be to know. I mean, that you have to have some kind of algebra that can tell you what this answer is beyond just what it is as an abstract group. And of course, you can specify generators, but that's, just in local number theory, if you aim to do that, that's typically not constructive. So,
I'm not sure whether constructive is a word I would agree with, but I think I understand what you mean. But getting hands on generator is constructive. At some point,
you can waive your input.
but I know what you. It doesn't reveal structure. I think that's probably what you mean. Yeah.
I think very early on you wrote for, I think it was 1 and 2, n equals 2 and p equals 2, that you had 2 copies of 2. Are there known constructions of finite complexes that give you those numbers?
You mean the Picard group for n equals 1 and p equals 2?
I think the next case up, n equals 2.
N equals 2, p equals 3? Well, I should say the only constructions known to me and to anybody I've talked to so far of elements in the Picard group are either, in terms of final things, are either suspensions of spheres or it's a truth.
Yeah, so there's no analog of the Joker for the next.
Nobody has come up with it.
You don't even know these elements are in the thick subcategory generator sphere.
No,
K
right.
and
Right. Well, that was the case.
found here, it should be called the punter.
Right,
Very interesting suggestion.
we should
Very seriously.
defer further conversation to coffee and biscuits.